Starks. It's a protocol family developed by Eli Ben Sasson, Michael Ryabtsev, Leo Goldberg, Alessandro, and others. And they went on to found Starkware, and they've developed high-quality variants and implementations of this protocol. And OpenZKP Stark is an independent, partial implementation of the variant used in the StarkDex alpha that was released about half a year ago. So Starks, what's so interesting about them? Well, first of all, they have a transparent, so a non-trusted setup. They have, I would argue, relatively simple math compared to some of the other zero-knowledge proof systems, although for most in the audience here, all of it should be fairly familiar by now. They have excellent prover and verifier performance, and they have relatively small proofs, not tiny, but small enough by modern internet data standards. But the coolest thing about them, and the main subject of my talk, is that they have a unique, completely different constraint system, and I say that with some irony. So what are Stark constraints? So you take your computation, you turn it into a computational trace. So like take all the intermediate values of all your operations, roll it out in a long table of a size that needs to be some power of 2 or some root of unity available in your field, but we're working with powers of 2 here. Then you pick a root of unity of the size, the length of your trace table, and for each column you create a polynomial that is interpolated on these values such that if I take omega to the power I and I feed that in my polynomial, I get the value in the trace table at row I in that particular column. I'll go into a concrete example soon, but just to give you a high-level overview. So now that we have this trace table committed to in polynomials, what we can do is define our constraints as rational expressions, algebraic expressions over these polynomials. And the standard way to do it is you write your expression such that it would evaluate to 0 on the rows where it holds, and then you divide out all the zeros of this polynomial. And this division will only be exact and result in a low-degree polynomial when the constraint indeed holds where it should. Now, concrete example, everyone's favorite one. Fibonacci. So we have this function. It takes 2 inputs, an index, which is like the nth Fibonacci number that we're interested in, and to make matters interesting, it also takes in a secret starting value. So we're not starting with 1, 1, we're starting with 1 secret. And then we iterate index times, and we update our Fibonacci and return the value at this particular index. So this is our problem. Now we can create an instance of this problem where we say, hey, we want the Fibonacci at index 200 starting with secret 42, and it just so happens to be this very large number here. All right. Now we want to create a zero-knowledge claim around this, and our claim is going to be this. We have a Fibonacci which has as input 200 and something that I'm not going to tell you, but the outcome will be this, and I'm going to prove you that I know what needs to go into these question marks. So first thing we do, we create the trace table. So it's really just you go through the algorithm, you take your variables, you tabulize their values, which looks like this. And then, so like you start with 1, and then your secret, and then 42, and then this value here, B, will be the sum of the other 2, and so on. We need to, at some point we'll hit 200, and we'll have in A our value that we return and want to prove. But since we're constrained to a power of 2, we need to extend this to the next highest power of 2. So we'll end up with 256 rows. So it needs to continue a little bit longer afterwards. Okay, this is our trace table. This encapsulates our computation. Now what do we do next? We have some constraints that need to hold on this trace table for it to be valid. For this particular instance of the problem, we need the reversed value to be 1. So like ti, 0. So like this is the trace table as a matrix. I would mean the generic row, which in this case is 0. I've split this out. You'll soon find out why. And 0 is the column. So first column, the row needs to, like the first column, the value needs to equal 1 on row 0. Another constraint is first column needs to equal our output value at row 200. These are so-called boundary constraints because they hold only on a single row. And then we have state transition constraints. So what we need is that row I plus 1 at column 0 needs to equal row I column 1. So this value here needs to equal this value here needs to equal this value, and so on. This needs to hold for all the rows. And then we have a constraint that says this value here needs to equal the sum of these two. That's this little thing here. Again, needs to hold on all these rows. Right. Next step, we interpolate this as two polynomials. So if you look here, the trace table itself didn't really change, but instead of it being some arbitrary matrix, it is now two polynomials, which are evaluated on these x coordinates, where omega is a root of unity of order 256. And if I were to take the first column polynomial, I would get my first column values back, second column is P1, and so on. Now that we have these polynomials, the next step is to convert these constraints into expressions that become low-degree polynomials when they hold. And there's a couple of steps involved in doing that. The first thing is to turn them into expressions that evaluate to 0 when they hold. This is very simple. We just subtract the right-hand side from the left-hand side, and we're pretty much done here. Next step, we need to turn them into expressions over the polynomial. So wherever you have ti, 0, we replace it by p0, x. Same thing here. Now, whenever you have ti plus 1, 0, like we have here, it turns into p0 omega times x. How does that work? Well, if this is my current x, the next x would be omega 4. So if I take x and multiply it by omega, I get the next value. So now we have this encoded. And this is also why we needed to stay in the abstract I domain instead of giving specific values, but because we need to have these x's in here. But we still have this thing over here that we need to incorporate in it. So first thing we can do is say that, okay, it needs to hold on these values of x. Again, pretty simple transformation. I just take omega to the power whatever numbers are here, and so on. Next thing that we do is that this expression is a polynomial that is supposed to be 0 at exactly this value of x. Same thing with this one. It is supposed to be 0 at exactly this value of x. And these two need to evaluate to 0 at all the values in this table. Right. In other words, this is a polynomial that can be divided by x minus omega to the power 0. And this one can be divided by x minus omega to the power 200. And this one can be divided by a little bit more complex expression, but let's show you the expression. So if it's in one row, I can multiply this thing by this expression, where I is like either 0 or 200, and the result would still be a polynomial. For the on every row constraint, instead of creating a really complex expression that has like multiple monomial terms in there for each one of these, it actually turns out that you can get all of these zeros together using just this one expression here. And this is kind of the critical thing that makes these error constraints efficient. If this efficient expression didn't exist, the verifier would still have to have linear time evaluating these things. There's one caveat though. This thing will also be 0 on the very last row, which is actually not what we want, because on the very last row, if you do x times omega, you'll actually end up on the first row again, and we'll have a constraint between the first row and the last row, which is not what we want. So what we do is we take that 1 point value, and put it back in the numerator to remove it from this thing. So now we have an expression that is 0 on everything except the last row, and we can divide it out from this thing. Okay. So we divide those out. And what we're left with now is these 4 expressions that will be low-degree polynomials if is what we want from it. So we've reduced our problem from our original claim from, hey, I know this Fibonacci question mark there, to, hey, I know of a trace table that satisfies these, that turns these 4 expressions into low-degree polynomials. So this is how errors work on a very low level. And we've implemented a start prover that can take these expressions and turn them in like a proper start prover and verifier in Rust. So what does it look like? If you want to code this up, there's basically, this is more or less the entire public API of the library, if you want to take the sort of syntax sugared interface. And what it is you have 2 traits that you can implement on your claim. In the first thing, in order to make something verifiable, we need to reduce it to a set of constraints, which is this function. It takes an object and then returns a set of constraints. The object is kind of arbitrary here. Returns a set of constraints. And if you give the library that, in return it will give you a function verify that takes in a proof and will tell you if the proof is valid or not. So that's all you need to implement the verifier. If you want to implement the prover, in addition to implementing the verifier, you also need to implement a function that will give you the trace table, which is also fairly straightforward. If you implement that function, in return it will give you a function that, given a witness, so like secret input, gives you the proof that then in turn can be verified using the verifier. Okay, how does that look like for the particular Fibonacci example? Now, first we implement our claim in a witness. The claim struct in our case is simply the index and the final return value. The index is a usize, an arbitrary number. The value is a field element. And then we have our secret, or witness, which is just a single field element, which we are going to put in the second step in the Fibonacci chain. Okay, so we have our 2 types that are relevant. Now we can implement our trace table. I'm going to start with the trace table because it's a little bit easier. You implement provable, given a witness for a claim. So self in this case would be the thing with index and value, and witness here would be our secret. So we initialize, we round the trace length up to the next power of 2. We create a new trace table of sufficient dimensions, in this case trace length and 2 columns. Is this one better? Sounds even more feedbacky. We initialize the first row to the values that we want. We iterate to the remainder of the row and basically just execute our Fibonacci algorithm as you would and return the trace. Next thing we need to do is implement the constraint function. So given a claim object, it has a function constraints that ultimately returns the constraints expression, but let's step through it. I'm including the rational expression class here, which does a bunch of things like overload the multiplication operator and basically makes the math intuitive. Again, we need to round up the trace length to the correct value. We need to compute our omega, which is a root of unity of sufficient, of size trace length. Then I'm creating 2 helper functions. One is onRow, which is basically this onRow expression that I showed. The other is every row, which doesn't take any input, but it returns this more complicated expression that is on every row except for the last. All right, given these helper things, now we can just return our constraints from expression. We pass our dimensions. We can put in a seed value that will act as a seed in the Fiat-Shamir transform in the prover. Let's ignore that for now. And then you give it a vector of all the constraints that you want to hold. So in this case, it is or this is the repeating constraint for the diagonal copy, which is on every row, so we just multiply it by that expression. The division is already happening there. Same thing with the Fibonacci addition constraint on every row. We have our first fixed value, and it needs to be 1 on row 0, and we need to have the output value at the row that we have on the index. This is also a good time to mention that Starks have a funny property that the constraint system is a function of the public input and not a function of the problem that you're trying to do, which gives you a little bit more flexibility, and haven't seen any actual practical uses of that, but it could be interesting. All right, so now that we have these, how do we actually use it? Very simple, actually. We just create a claim object, and we create our witness object, and then we can do claim.proof given this witness, and there is your proof. And then we can serialize this proof to bytes, or we can use it immediately here and just do claim.verify, and this function will return an error when something's wrong. Okay, so that's how you do a Fibonacci proof. I still have a little bit of time left, so we can do one more thing. So let's go into Mimsy, which is interesting in its own right. So Mimsy has some constants. Let's say in this case it has 16 constants. It takes an input, it cubes it, adds a constant, repeat it through the list, and then returns it, right? So we only have one variable, so we end up doing this with one column. And we'll end up having a constraint that looks like this. The next value is the cube of the previous value plus this constant, which should be repeated. The reason I'm bringing it up is because this is a cubic example, which is a little bit different, although mostly in the prover end, and because it has this repeating pattern in there, which is interesting. So how are we going to handle that? Well, first, we can do the straightforward conversion to polynomial forms of columns. It works, but what do we do with this k here? Let's look at it a little bit more. Let's say, so here's how you can solve this. So let's say we have these values of x. We want to somehow get access to values that are a repeating pattern of these 16 values that we have here. So let's first look at x to the power 16. If you look at what this does to the value of x, you'll see that it has this structure of omega to the power 0, omega to the power 16, and so on, all the way to omega to the power 240, which will already happen at omega to the power 16 here. It will be at 240 here, and then it will wrap around, and we will have at omega to the power, the next one, we would have omega 0 here again, and this would cycle and cycle until the last row where omega to the power 255 would correspond again to omega to the power 240. So basically, we've already created a repeating pattern of our omegas here. This is a repeating pattern with 16 values in it, and it repeats 16 times to pad it out to 256 values. Okay, now we can take a polynomial over that value, which will have, let's say this is some arbitrary polynomial. It will have 16 different values here, and then it's pretty much forced to cycle because its input cycles. So the next one will be repeated again, and so on. Which means that we can interpolate this and come up with some degree 15 polynomial that gives us a repeating pattern with exactly the values that we need in order to satisfy the constraint that we want. So this gives us the answer. We have this degree 15 polynomial expression over x, which we can evaluate over x to the power 16, and then we have our constraint expression again. And now we can kind of forget about the numbers in the beginning. We don't really need them. Like in the end, you'll still have a trace table that only has one column. You just end up with a more complex constraint expression here. And the remainder of Mimsy is nearly identical to Fibonacci. You need to divide out the zeros where you want the constraint to hold. You need to have an input and an output. boundary constraint, but it's pretty straightforward from here. So this is where our library is right now with our Stark implementation. So some of the future directions that we want to do is have constraints that go over multiple rows. So right now we were limited in our examples to the current row and the next one. Future things would be to have longer offsets where you can refer back to values further back. And actually this change just got in this week, so you can already do that. We have more examples in our system. We have Mimsy implemented. We're working on a VDF implementation. We want to build EVM verifier contracts, ideally automatically generated from the constraint system. Higher level language will be interesting because, as you saw, this is a pretty low level and awkward way of dealing with things. There was just a really great talk on AirScript, which is a very promising direction in doing this, so we'll probably end up implementing that. Performance should already be pretty good, but you know, it can always be better. We love to optimize this stuff, and in fact, it seems viable to implement this on GPUs or even FPGAs to get more performance. And another thing is that it has a good FRI implementation, low degree testing implementation, so it should also be doable to implement transparent, no trusted setup, Marlin, Plonk, Fractal, etc. on it, which would be an interesting direction. And of course, it's open source, and you're all invited to contribute your ideas and code and issues. So yeah, thank you very much.